Acho que agora já está. Já está, mas não se viu o micro. Porque não era aqui. Select the speaker. Vou estar a usar aqui. Não, isso para quem se lava. Pronto, para ouvir. Porque o speaker devia ser este, mas não aparece aqui. Microphone. E vamos ver se está também. E esse também. Sim. Mas. Agora? Não. Tem problema com o nome. Alô, alô? O que está aqui? São eles que estão. Teste? Pois. Não, vamos ver sair por ali. Isso é colocamos no. Isso também aconteceu ontem. Senhor? Também aconteceu ontem. Não. Ontem não. Eu tocava com uma lágrima. Teste. someone called to desculpa. Não sei o que é que dizer. Não, não está bem. O problema é com o som. Agora também não há experimentar. Sim, ela faz as coisas. Bem, olha. Eu desliguei este, vai? Desliga este. Este é o problema. Eu acho que podia ser daqui, porque eu ouvi daqui. Eu pus este, quer dizer, pus no mute. Ok, funciona ou não? Not really. Does this work? No, I'm not pensando. I don't think is it working? Okay, okay. Okay, so. Okay, so our next from technical department, she will tell us about conformally Kähler, Einstein matrix from ODEs. Okay, so let me start by thanking Giordano for inviting me. I am outside of my area of expertise in speaking to you. So if ever there is a question or some background which I'm not thinking of giving, please let me know. I mean, I'm happy to give more. Okay, so let me start with a bit of with some background. So the first thing I'm going to do is define for you an Einstein metric, and this is a definition within the realm of Riemannian geometry. So you start with a Riemannian manifold. This is said to be Einstein if there's a constant such that the Ricci tensor is a multiple of the metric. So an Einstein metric is one for which the Ricci tensor is proportional to the metric. And so why do mathematicians study this? Well, the first little calculation that should motivate the study of this is the following. So the Ricci tensor being proportional to the metric means this, and then this implies I can trace the Ricci tensor, which gives me this. And so this is meant to show you that Einstein metrics have constant scalar curvature, and constant scalar curvature metrics are of interest in Riemannian geometry. So this is one of the reasons why we care. But there's actually lots more reasons why we care. And so let me sort of sum up for you something that's said in the introduction of so very influential Riemannian geometry book called Einstein Manifolds. It's kind of 500-page book just about this equation. And they here are the reasons they give. So first of all, you should care if you care about topology, because there are topological obstructions to existence of these metrics. So there are topological obstructions to existence. So these metrics reflect, in some sense, some of the topology of your underlying space. Okay, so for me, the second reason is you should care if you care about geometry, because this equation is canonical. So these metrics are canonical, or in some sense best, if you care to say that. So their properties reflect the geometry. Okay, so this is why I care, for instance. So there are, these metrics are also interesting to people studying PDEs, not only because the PDE itself is really interesting, but because it relates to other PDEs that people care about. And a famous instance for this one, it relates to the Young-Mills PDE in sort of a meaningful way. So you should care if you care about PDEs. And lastly, you should care if you care about physics, and for several reasons. So it's obviously an interesting equation if it comes from relativity. So it's interesting there. But more relevant for me for today's talk is that the metrics that will show up are sort of objects of interest. In something that Witten called the ADF-CFT correspondence. So for many reasons in physics, people care about these metrics. Okay, so if you agree to care about Einstein metrics, then you sort of have to care a little bit, at least, about Kähler geometry, because Kähler geometry is sort of our greatest source of Einstein metrics. Most of the metrics we know that are Einstein come from Kähler geometry. So it's a source of examples and a source of understanding. Okay, so I mean, I'm not sure what to do here. So I was going to define for you Kähler manifolds, but it's kind of an unfair thing to do, because either you have seen them and this will be boring, or I don't think the definition itself sort of elucidates what they're good for. But a Kähler manifold is actually a complex manifold with some extra structure, which can be encoded in two ways. So one is a symplectic form, which is a closed two form, which is non-degenerate. And it can also be encoded by a Riemannian metric, but the two must be compatible in a sense. So omega is J invariant, and the metric arises from the form in this way. So, and in fact, it's actually an extra condition that this must be positive definite. This must be a metric for your, this is the definition of a Kähler manifold. So it's essentially a complex manifold which is also symplectic, or which is also Riemannian. Okay, and so I'm sure you all know examples because some common manifolds are Kähler. So Cn is an obvious example, projective spaces, and subvarieties in projective spaces, complex projective spaces are examples. Okay, so the Einstein equation sort of simplifies in the Kähler setting because of the following. So suppose you have a Kähler manifold. Then we say that this is Kähler-Einstein if there is a constant such that this and this row is what we call the Ricci tensor. It's actually a 1-1 form, and I can very quickly define it for you. And it for I guess non-obvious reasons, but not that hard. It sort of encapsulates all of Ricci. So somehow this is the simplifying thing that happens in Kähler geometry. We can package the Ricci tensor very nicely. Okay, and so this condition, in fact, implies something quite strong. It restricts the class of the form. So for a Kähler-Einstein metric, so these two forms are closed, and so they define a cohomology, and their cohomologies must be related in this way. And the cohomology of the Ricci is actually the first Chern class of the underlying complex manifold. And so if a Kähler-Einstein metric exists, it lives in a multiple of the first Chern class of your Kähler manifold. So there's sort of a serious restriction there. Okay, so examples are, of course, all of the projective spaces with their usual complex structure and the Fubini-Studi metrics. These have lambda equals to 1. And there's another famous instance of Kähler-Einstein problem that arises in that you may have heard of. When lambda is equal to 0, the existence of such metrics sort of awarded Yau his Fields Medal. It's the Calabi's conjecture. So it was settled by Yau. Okay, but I'm going to focus on the positive case, and I may as well assume that lambda is 1. So this is called the Fano case. And so which case you fall into is a Kähler invariant. It depends on your complex structure. Okay. So in this case, there are manifolds which do not carry. We know this. Kähler-Einstein metrics. Okay, and so examples, and these two are going to play a really important role in everything I say, are one blow up of CP2. So the blow up of CP2 at one point. This is a complex manifold, and I even if you don't know it, I will say more about it. So maybe you actually know it and don't think so. And this is another example, two blowups of CP2. These two do not carry Kähler-Einstein metric. We've known that for a long time. Okay, so I guess that the guiding question is what to do to find Einstein metrics there. Okay, so think of that as the guiding question for today's talk. Okay, so there's actually kind of two options and two ways in which people have approached this question. You can either sort of relax the Einstein equation. You can say, okay, I don't mind sort of a good metric, even if it's not Einstein, or you can relax the Kähler. Either relax Einstein or you can relax Kähler. And you say, well, maybe I want an Einstein, but not Kähler, which is the spirit in which I'm going to talk about. But I'm actually, I need to discuss the two options. Okay, so this brings me to my next topic, which is Calabi's metrics. And this is kind of an option one sort of discussion. And again, this starts with the definition, which is an important definition in Kähler geometry. It has played a really big role, and it's due to Calabi. Definition is the following: suppose you have a compact Kähler manifold. And then the sort of metrics he's interested in are the following. So this is extremal, and now people say Calabi or Calabi extremal. If it is a critical point for a very natural functional, which is the following. So first of all, it's defined on your Kähler class and on the Kähler cone. The Kähler cone means the forms that are actually Kähler. And it's simply the total scalar curvature of a metric. So Calabi metrics or extremal metrics are metrics which are extremal for the total scalar curvature. So I think it's a pretty reasonable definition. You want to square? This is a topological invariant without the square. Okay, and I guess the okay, so first of all, to make any sense of this is a reasonable definition, but to make any sense of this, to be able to do anything, you sort of need to understand what this means in more concrete terms. So people derive the Euler-Lagrange equations. It's pretty simple, and the Euler-Lagrange equations just say that a metric is extremal, or a form is extremal, if it satisfies the following. And the reason why I write this is that to make it clear that this works in the non-compact setting, and that matters to me, but also because it makes clear that constant scalar curvature, then, if your constant scalar curvature, this is constant, and so whatever this means, it should be zero. So constant scalar curvature implies extremal. And therefore, Kähler-Einstein, which I have tried to explain, implies constant scalar curvature, also implies extremal. So this does generalize the Einstein condition. Okay, and so I guess the question then that you should that it's natural to ask is, do these always exist? And this has been a driving question in Kähler geometry for the last 40 years, and the answer is no. And there's a famous conjecture around this story, which is the Tianyao-Donaldson conjecture. And this is, so a Kähler manifold admits an extremal metric in its class if and only if it is k-stable. And I'm not going to go into the definition of that, but it's purely algebraic, or you can define it in purely algebraic terms. And it's fairly involved, but it's well understood by now. And so what I do want to say is that this has been settled in the Kähler-Einstein case by so it's a famous series of papers by Chen, Donaldson, and so. So they know this holds there, and so we are completely we understand the existence problem for Kähler-Einstein metrics fairly well by now. Okay, or as well as we understand k-stability. Yes. Mm-hmm.
So did you mention
What the sorry?
What you wanted to reductions there?
Yes. But it's restricted to a subset of the space of all metrics, which is rather special. So its critical points are different from what you think. That's right. And this is a serious restriction because all of the metrics here are of the form are like this. So it's not what you think.
And then when there's also second question.
Yes. Yes.
Yes, so the Donaldson conjecture would be zero for Kähler-Einstein.
No, because the question is, does it exist? If it's Kähler-Einstein, it's extremal, but we don't know whether extremal exists. We don't know. This is open. We do know, after a lot of effort, when Kähler-Einstein exists.
Okay, but what's the last statement?
So the Tianyao-Donaldson, this Tianyao-Donaldson conjecture has been settled in the Kähler-Einstein case, meaning that we know that a Kähler-Einstein metric exists in the class C1 if and only if your underlying manifold is k-stable.
If not only.
Yes.
Well, then it seems that the conjecture is solved.
Is what?
And stating it like that, it seems that the conjecture is right, because if it's k-stable, then it meets a Kähler-Einstein.
Well, but only in the case when the class is right. There's no, okay, so another way to say this is Tianyao-Donaldson has been settled. It's a particular choice of class for which has been. In when omega is C1, not in general. Okay, it seems like a small difference, but it's not.
Depends on the cohomology.
Yes. Yes, it depends on the Kähler structure. Yes. Mhm.
Then it seems
And it's really true.
to say then if you are in the monotone case like that,
Yes.
and if
Monotone case means that omega
omega
is,
is equal to 0,
yes,
and if it's case stable,
then it has a Kähler-Einstein metric. Yeah.
no, but the conjecture say so there are no cases when you have an extremal not Kähler-Einstein metric when C1 is equal to omega.
Well, existence depends on case stability.
So if it's case stable, monotone, then the metric is actually Einstein,
Yes.
not extreme.
Yes. That's true. That's right.
That seems.
In fact, okay, so maybe what helps.
It's not extremal metric.
Okay, wait a
That
second.
is-
I think
that is Einstein
extremal.
in the monotone case. It's not correct.
Does this help?
So take your example, right? CP2 don't have that one, for example.
There is no metric,
It's extremal metric.
but not in C1.
No, there is extremal metric in C1 is equal to omega.
No, there's no extremal metric. There isn't. I mean, the Calabi metrics there are not Kähler-Einstein. We know they're not Kähler-Einstein because the automorphism. It's not. It's not. It's not. It's not. The automorphism. No, maybe. So the case stability depends on the whole Kähler information. It does not only depend on MJ. It depends on the class where you're looking for your. Is not case stable. Yes, but not in C1. No, not in C1.
It has an extremal metric in C1.
No. No, well, we can discuss it. It's not. So the case stability depends on the class. I sort of. Are there more questions?
How you find the extraction can be scaled by any number, right?
Yes, and the class varies with scaling.
By any ratio, and any real number.
Yes, the class varies.
But then the point, it's like proportionals from equal to 0, so on and so forth.
No, but that's, I mean, whether your C1 is positive definite or negative definite or 0 is topological. It's not topological, but it depends on MJ.
Also, only the equal C1 is positive coefficient or exactly is coefficient 1.
It doesn't matter.
So it doesn't matter. Any coefficient non-zero.
Yes.
So the only
No, I mean with the fixed sign. If it's negative, that's another. There's three options. Are there more questions? Okay, so okay, so the okay, so one thing I do want to say is that okay, we not only understand this very well, but actually we have explicit examples that are due to Calabi. And so let me sort of, he has an ansatz, a very broad ansatz, of which I only need a baby version. It's called the Calabi ansatz, but I'm going to state it in far less generality than it actually gives. Suppose you have so the story is as follows. There is a 2-parameter family. So there is a 2-parameter family of metrics, of extremal metrics. And well, let me state it like this. In a disk bundle So this is a disk bundle. So in the total space of a disk bundle of Chern class N over S2. Okay, so this is so O of minus N for me is the tautological bundle over S2. And you know, O of minus M is just its tensor power. And the disk bundle is sitting inside of there. So its fibers are disks over S2. And Calabi has built metrics on the total space of that. And as a consequence, well, he got the first known examples of extremal non-CSCK compact matrix or Kähler matrix. And he got those on what we call Hirzebruch surfaces, which are kind of related to the disk bundle. They are the projectivization of these O of M's. So this is a bundle over S2 whose fiber is a projective space. And this is where he built his metrics. And it just so happens that H1 is one blow up of CP2. So his ansatz gives an extremal metric here. An explicit one. We know it explicitly in coordinates. Okay, so let me sort of move on to option 2. Which is
there's no M in the event.
No, this one here is the only record. Oh, yes, absolutely. Thank you. Yes, that's good. So conformally Kähler metrics, which is kind of in the spirit of option 2, relax the Kähler condition. And so let me sort of give a quick definition. If you have a Riemannian manifold, then we say that this is, you know, conformally Kähler or conformally Einstein or conformally whatever you want. If there is a smooth function and a starting either Kähler or Einstein or whatever you want metric, such that the two are related via a conformal factor. And so this is our definition. And I also need to define or remind you, either define or remind you what the Weil tensor is. The Weil tensor is it's a 3-1 tensor, which measures conformal flatness. So this tensor is designed so that the Weil tensor of a metric is 0 if and only if G is locally conformally flat. So conformally flat, you should be able to guess from this, and locally just means replace sigma on the whole manifold by sigma on open sets. Okay, so this is a Weil tensor if the manifold is compact, if the Riemannian manifold is compact, we define the Weyl energy to be the total Weyl tensor. This is what we call the Weyl energy. And these quantities are conformally invariant. Okay, and so in fact, the reason why I mentioned this is that we do know, and it's been known for quite some time, we know that CP2 blown up at one point, that is the first Hirzebruch surface, admits a conformally Kähler Einstein metric, which was constructed by Page, who was a physicist. And maybe following this metric of Page, Derdziński asked the following question. In the 80s, he asked, when is Kähler manifold conformally Einstein? Okay, so it's a question that makes sense for us if we're looking for Einstein metrics, and because, well, you might get Einstein metrics that are conformal to a Kähler one, and he actually answered this question. In the form of a theorem. So the theorem is the following. So suppose you have a Kähler manifold, and suppose that the scalar curvature of the corresponding metric is not identically zero. Then this is conformally Einstein. That is, there is an Einstein metric in its conformal class if it is Bach flat, and I owe you a definition of Bach flatness, which I will give. And in this case, he actually tells you what the Einstein metric is in the conformal class. It's the starting metric over the square of the scalar curvature. This is Einstein for defined. Okay, and
Those extreme, right?
no, but so this is Bach flat implies extremal. This is a lemma. But the converse is false. Oh. Okay. So this theorem of Derdziński then sort of should point to you that if you care about Einstein metrics, then Kähler Bach flat metrics are interesting, whatever that means. And so I will define for you, hoping that you care about them, or you see why I care about them. I will define Bach flatness for you. It's very simple to define. So it's actually in the realm of Riemannian geometry. So suppose you have a compact Riemannian manifold is Bach flat if it is a critical point for the Weyl energy. Okay, so Bach flat metrics are those which are critical for the total Weyl curvature, which is also, I think, a natural condition. But again, as in the extremal case, it's you can't work with such a thing. You need to write down the Euler-Lagrange equations. And the Euler-Lagrange equations are there's a certain tensor that appears. Which is called the Bach tensor. And I want to write it down for you because it makes something obvious. So the Bach tensor is defined in the following way. It's this, where this Ricci zero is traceless Ricci. That is, it's the part of Ricci without a metric direction. And so it's exactly so that it vanishes on Einstein metrics. And the reason why I write the Bach tensor for you is that this should show that if G is Einstein, then G is Bach flat, because if G is Einstein, this Ricci zero vanishes. So for just on the nose, Einsteins are Bach flat. And then if you believe me when I say that the Weyl tensor is conformally invariant, then if G is conformally Einstein, then it also implies that it's Bach flat. And this shows sort of the easy part of Derdziński's theorem. There is one implication here that's very easy. The other one is not as easy. Okay, are there questions? So Bach flatness is that. You can test it with a tensor. Okay, so let me come to what I want to say now. So I kind of want to discuss our results. So all of the results are joined with Rosa Oliveira, who is sitting there. And the results come from the quest for Einstein metrics, and they come from sort of the following simple idea. So the reason why I mentioned the Tian-Yau-Donaldson conjecture in the Kähler-Einstein case is that so Tian-Yau-Donaldson in Kähler-Einstein was settled via a continuity method involving cone angle metrics. And so I guess because of this, cone angle metrics, so metrics which have a cone angle along the divisor. So they're singular metrics, but they're mildly singular. We control how singular they are, and they are only singular along a divisor. So these metrics appeared in Kähler geometry. Well, I guess they appeared before, but they kind of became prominent in Kähler geometry after they appeared in this settling of this big conjecture. Kähler geometries now care about such metrics. And somehow this fact inspired our quest. So here was the idea. Here was our initial idea with Gaussard. Again. So Calabi's ansatz, so Calabi's metrics on these Hirzebruch surfaces are not Bach flat, except for H1, where we know they are, and it's a special case anyway, so are not Bach flat for m equals to 1. So it's not like we can use them to produce Einstein metrics because they're not Bach flat, but so our idea was we add a cone angle along a certain canonical, along what we call the divisor at infinity. And so the idea is we want to choose it so that the metric is Bach flat. So there is a 2-parameter family from Calabi. We carry out Calabi with a cone angle. It's not much harder than usual Calabi. It's an ODE with a singular behavior at the boundary. And we just choose the cone angle so that the singular metric is Bach flat. And then we need to divide by the scalar curvature. And the hope is that the scalar vanishes before what we call before the cone angle. So the resulting, and remember, we need to divide by the scalar anyway. So the hope is that if the scalar vanishes before the cone angle, the resulting metrics are not, don't see it. So they are singular, but they don't see the cone angle, and they are singular in a very well understood, controlled way. They're singular because of the division by scale, which, if I have time, I will discuss. So essentially, this work, this idea essentially worked. And let me state the theorem in a more precise way. So how much time do I have?
10 minutes.
10 minutes. Okay, a bit less, right? A bit more. Okay, 12 minutes. Okay. So so the theorem, to state something precise. So first of all, so for n equals 1, things are different. What we show here is that for all cone angles in this interval, there is a cone angle, there is an Einstein metric with a cone angle beta along the divisor at infinity. So for m equals 1, we are able to produce cone angle Einstein metrics. Okay, so for n greater or equal than 3, what we produce is very different. So what we show is that there are 2 metrics which are Poincaré-Einstein. So they're Einstein, and I will explain what Poincaré-Einstein means in a second. I owe you a definition of this, but think of Einstein for now. We produce 2 metrics, they're Poincaré-Einstein, whose conformal infinity, and again, I owe you a definition of this, is the boundary of this. Okay, and GM plus is smooth, whereas GM minus is never smooth. It either has a cone angle or it's incomplete. Okay, so this is the theorem, and so sort of to understand, to explain the significance of this, let me discuss what these Poincaré-Einstein metrics are. So actually, you know a Poincaré-Einstein metric very well. The standard example, or the first example, is the hyperbolic metric on an n ball. So a definition is as follows. So suppose you have a Riemannian manifold with boundary, and suppose you have a defining, let's call it a defining function for your boundary. That is, your boundary is defined as a level set of your function, and df is not 0. Then G is Poincaré-Einstein if two things. First of all, it's Einstein on the interior of the manifold. And then it has a certain behavior on the boundary, which I will describe to you. So rho squared G or F squared G extends to the boundary. Okay, and so in this setting, this F squared G is not well defined because it depends on the defining function. And of course, I could always multiply my F by a nowhere vanishing constant. This F is not an intrinsic quantity, but the conformal class of this thing is well defined. It's independent. It's independent of the F, and it's called the conformal infinity. And this G is called a filling. So, sorry, the conformal class of the restriction to the boundary is well defined. And G is a filling. It's called the filling of this conformal class. Okay, so what we have done can be phrased in these terms. What we have done is we constructed fillings of the boundary of the disk bundle. And the boundary of the disk bundle, this was something I learned from Miguel, is S3 mod Zn. And the class where we constructed is the class of the Berger metrics in here. So we constructed a filling of this. We constructed two fillings. Well, one of them is smooth. So GM plus is a smooth filling, while GM minus is not. Okay, so Poincaré-Einstein metrics are have been extensively studied. As I've said, the hyperbolic metric on the ball is an example. There are like local existence results that are due to Pfefferman. There are non-uniqueness results of fillings that are due to Anderson. And so these are the metrics. These are the metrics that appear on one side of the ADS CFT correspondence. And as a consequence, physicists have tried really hard to build examples of these metrics. And so Page and Pope have constructed or have a filling of the same space of this S3 mod Zn that they had constructed, and it looked different from ours. And we knew that these fillings didn't have to be unique. So for a while, we thought we had a different filling. But in fact, it turns out, because it follows from actually simple results from a result of Derdziński and some easy remarks. So their metrics, it turns out that theirs is isometric to GM plus. So GM minus is new, but it's singular. and GM plus is smooth, but it's not new. So we were perhaps a bit disappointed at this point, but we still thought that the construction, the construction is different, and we thought it was a worthy construction because we include metrics with a very different behavior in one family. Okay, so that's one of the upshots. And so we set, okay, so there's kind of an interest among geometers for degenerating families of Einstein metrics. And because we have a family, we decided that we could degenerate our family and see what happens. So we calculated limits. Okay, so this is the last thing I want to say. So in calculating these limits, we found two things. So first of all, for n equals 1, the zero cone angle limit, which is often the limit geometers care about, also in relation to Tianyao-Donaldson conjecture. But the zero cone angle limit of our metrics actually recovers another metric which was known to physicists. So it's the Kerr-Bolt, or is among the Kerr-Bolt family. It's Kerr-Bolt, okay? So it's kind of a way to see Kerr-Bolt as linked to other known metrics. So this is how you can think of this limiting result. It's there. We give a path between Kerr-Bolt and some very different looking metrics. Okay, but what I do want to emphasize is the following. So for m greater or equal than 3, it just turns out that one of the rescaled limits, sort of a certain rescaled limit, which I can't describe to you because I didn't give you enough information about the construction. But a rescaled limit gives an Einstein metric which is actually conformal to a scalar flat Kähler metric. So it cannot come. It cannot come from Derdziński. Okay, so I guess the question which I want to leave is so I would like to ask about this metric. So there are physicists in the audience, so maybe they know. So is this metric new? And otherwise, I would also like to ask the following. So we know lots and lots of scalar flat Kähler metrics concretely. And so if this metric is new and if this construction is interesting, is this a good way? Is this a good method? Can we use the scalar flat Kähler metrics we know to construct Einstein metrics? So is this a good way? I mean, anyway, I don't need good. Is this a way to construct Einstein metrics? Okay, so as far as we know, it might be true that the metrics are new, but we are not really sure. Okay, I hope I didn't go over time. So this is all I wanted to say. Thank you.
Is there any question or comment?
Okay. What is metrics you guys constructed, are they all homogeneity, meaning they all come?
They're all homogeneity one. That's something I would have liked to discuss more because we're in an ODEs correspondence. So all of these metrics come from solving an ODE. All of them. Well, the Kähler one do. The other ones, no, but they're still homogeneity one. The Kähler ones, the extremal ones, come from what you know very well. They come from an ODE. The other ones are conformally related.
Formal factor is also invariant.
Yes, they are. You want to invariant. They don't solve an ODE. Yes, they are homogeneity one. Yes.
So if there are no further questions, let's thank the speakers.
Thank you.